Somewhere in our galaxy, a dead star no wider than a city is holding a secret that could outshine the sun many trillions of times over, and unleash all of it in less than a second. This isn't a star exploding. The star survives. Yet in one blinding flash, it can flood space with more high-energy radiation than our sun pours out in 100,000 years, briefly reaching across tens of thousands of light years to rattle satellites and instruments here on Earth. What could make a stellar corpse the size of a town suddenly convulse with that kind of fury? The answer isn't nuclear fire, it's magnetism, wound so impossibly tight that it can crack the star itself. Tonight, we're going to find out what a magnetar really is. Before we get into it, if you enjoy slow, careful journeys into the strangest objects in the universe, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let me start with a single, stubborn contradiction, because everything we're going to explore tonight grows out of it. Somewhere out in the galaxy, there is an object that is dead, and yet violently alive. It is dead in the sense that it no longer burns fuel the way a normal star does. It has already lived, already collapsed, already been left behind as a corpse, and it is only about the size of a city. If you could somehow set it down on Earth, it would fit comfortably inside a large metropolitan area, tucked between the outer suburbs. And yet this small dead thing can, without any warning, convulse and release a flood of radiation so intense that instruments across tens of thousands of light years feel the shock. It does not explode to do this. It does not tear itself apart. It simply rearranges something invisible wrapped around and through it, and in doing so, it briefly becomes one of the most violent objects in the known universe. That invisible thing is a magnetic field. Not an ordinary magnetic field, but a magnetic field so extreme that it defies almost every comparison we can reach for. And the object that carries it, the one we're going to spend our time with tonight, is called a magnetar. Before we can understand what makes a magnetar so strange, we have to be clear about what it actually is, because there's a common misconception worth clearing up right away. A magnetar is not some exotic, separate category of object with no relationship to anything else in the cosmic zoo. A magnetar is a neutron star. That's the key. It belongs to a family we already know something about. It is a specific, rare, extreme variety of neutron star, one that happens to carry an almost unimaginably powerful magnetic field. Everything unusual about a magnetar, everything terrifying and violent and beautiful about it, comes down to that one added ingredient. Take an ordinary neutron star, wrap it in a magnetic field thousands of times stronger than the already strong fields most neutron stars possess, and you have a magnetar. So to understand the magnetar, we first have to understand the neutron star it's built from. Neutron stars are what certain massive stars leave behind when they die. Now, most stars, including our own sun, will never become neutron stars. They're simply not heavy enough. Our sun will end its life quietly, swelling into a red giant and then shedding its outer layers to leave behind a slowly cooling ember called a white dwarf. But the story is very different for stars far more massive than the sun, the true giants. Stars with perhaps 8, 10, 20 times the mass of our own star. These stars live fast and burn hard. They fuse hydrogen into helium, then helium into carbon, then carbon into heavier elements still, working their way up the ladder of the periodic table, forging heavier and heavier nuclei in their cores. And this fusion is what holds them up. The outward push of all that energy balances against the relentless inward pull of the star's own gravity. For millions of years, That balance holds, but it can't hold forever. Eventually, the core of such a star fills with iron, and iron is the end of the road. Fusing iron does not release energy, it absorbs it. So when the core becomes iron, the furnace that held the star up for millions of years simply switches off, and in that instant, gravity wins. The core, which had been supported by the pressure of its own fusion, suddenly has nothing holding it up. It collapses, and it collapses with breathtaking speed. In a fraction of a second, a core larger than the Earth crushes down to a ball only a few dozen kilometers across. The infalling material slams into this newly formed core and rebounds, and the outer layers of the star are blasted away in one of the most powerful explosions in the universe, a supernova. For a few weeks, that single dying star can outshine an entire galaxy of hundreds of billions of ordinary stars. We're going to keep the supernova brief because the explosion itself, dramatic as it is not really our subject tonight. What matters for us is what gets left behind at the center after the fireworks fade. Because when that core collapses, something extraordinary happens to the matter inside it. The gravitational crush becomes so extreme that it forces electrons and protons together, merging them into neutrons. The entire core becomes, in effect, one gigantic mass of tightly packed neutrons, held up not by fusion, not by heat, but by a strange quantum rule that resists packing particles too closely together. That object, that ball of pure crushed neutron matter, is the neutron star. And it is unlike anything in ordinary experience. A neutron star is roughly 20 kilometers across, about the width of a city. But packed into that small sphere is more mass than our entire sun. Think about that for a moment. The sun is about 1,300,000 times the volume of the Earth. And you're taking more than all of that mass and squeezing it into a ball you could drive across in 20 minutes. The density this produces is almost impossible to describe. A single teaspoon of neutron star material would weigh somewhere around 1 billion tons here on Earth. 1 teaspoon. That's the weight of a mountain packed into a spoon. The surface gravity is so intense that if you could somehow stand on a neutron star, you would be flattened instantly, spread across its surface, thinner than a sheet of paper. This is matter pushed to the absolute edge of what the laws of physics will permit before collapsing all the way into a black hole. So that's the raw material. A neutron star is already one of the most extreme objects that exists. It spins, often rapidly, sometimes hundreds of times every single second, whipping around faster than a kitchen blender. It carries a magnetic field, and here we arrive at the crucial fork in the road. Because most neutron stars, the ordinary ones, already have magnetic fields that would astonish any engineer on Earth. A typical young neutron star might carry a field of around 100 million Tesla. And to understand why that number matters, we need something to compare it against. So let me build a ladder of magnets from the familiar all the way up to the impossible. Start with something in your own home. A refrigerator magnet. The little decorative kind holding a photo to your fridge door has a magnetic field strength of roughly 1/100th of a Tesla, give or take. It's just strong enough to cling to metal. That's our first rung, something you can hold in your hand. Now climb higher. Go to a hospital and step into the room with a magnetic resonance imaging machine, an MRI scanner. Those machines use magnetic fields of around 1.5 to 3 Tesla, hundreds of times stronger than your fridge magnet. They're strong enough that a stray metal tool can be ripped across the room and turned into a projectile, Hospitals post serious warnings about them for exactly that reason. That's a genuinely powerful magnet, one of the strongest most people will ever encounter in daily life. Now let's climb well beyond everyday life into the world of specialized laboratories. Physicists who study materials under extreme conditions build enormous, purpose-designed electromagnets. The strongest continuous magnetic fields humans can sustain in a laboratory reach somewhere around 45 Tesla. And with special pulsed magnets, ones that fire a field for only a tiny fraction of a second before the coils would tear themselves apart, researchers have briefly reached fields of 1,000 Tesla or even more, though the equipment sometimes destroys itself in the process. So 1,000 Tesla represents roughly the practical ceiling of what human technology can produce, and even then only for a flicker of time before the magnet blows apart under its own strain. Hold that number in your mind. 1,000 Tesla, the very limit of human engineering, achieved only for an instant with magnets that self-destruct. Now, compare it to an ordinary neutron star, which sits calmly with a field of about 100 million Tesla, day after day, year after year. That is 100,000 times stronger than the strongest field we can briefly force into existence on Earth before our best magnets tear apart. An ordinary neutron star is already so far beyond our reach that the comparison starts to feel absurd. And an ordinary neutron star is not our subject tonight, because a magnetar takes that already staggering field and multiplies it again. The magnetic field at the surface of a magnetar can reach something like 10 billion Tesla, and in the most extreme cases, perhaps 100 billion Tesla. Let me put that beside the ladder we just built. The strongest field human technology can momentarily produce is around 1,000 Tesla. A magnetar's field is roughly 100 billion Tesla. That is about 100 million times stronger than anything we can make. And it isn't a fleeting pulse from a self-destructing coil. It's the steady, permanent state of the object. A magnetar simply sits in space wrapped in a magnetic field 100 million times more powerful than the best magnet humanity has ever built, and it holds that field for thousands of years. These numbers are so large that they almost stop meaning anything. So let me try to make them physical instead. A magnetar's magnetic field is so strong that it would be lethal from a great distance, not because of radiation, but because of magnetism alone. If you brought a human being within about 1,000 kilometers of a magnetar, the field would begin to distort the very atoms in your body. Atoms are normally roughly spherical, with their electron clouds arranged in gentle, balanced shapes. But in a field that's strong, atoms get squeezed. They're stretched into thin, elongated cigar shapes, because the magnetic force overwhelms the ordinary electrical forces that give atoms their structure. And once you rearrange the atoms, you rearrange all the chemistry that depends on them. Every molecule in your body, every protein, every strand of the machinery that keeps you alive depends on atoms having their normal shapes. In a magnetar's field, that chemistry simply cannot function. You would not be burned or crushed. Your biochemistry would just quietly cease to work, because the atoms you're made of would no longer be the right shape to be you. That is what a magnetic field of that strength does to matter. It doesn't just push on things, it rewrites them. And the effects reach far beyond the star itself. Even at a distance where a human being would be safe, a magnetar's field can influence the behavior of atoms and the propagation of light in ways that show up in careful measurements. The magnetic field wraps around the star and extends outward into the surrounding space, threading through the thin plasma there, shaping how charged particles move for thousands of kilometers in every direction. The magnetar is not just a small, dense ball, it's a small, dense ball at the heart of an enormous, invisible, and almost incomprehensibly powerful magnetic structure. Now, how many of these things are out there? This is worth pausing on because magnetars are genuinely rare, and their rarity is part of their story. Our galaxy contains somewhere between 100 billion and 400 billion stars, and it holds an enormous population of ordinary neutron stars, likely hundreds of millions of them, scattered across the galaxy as the remnants of ancient dead stars. But confirmed magnetars? We know of only about 30. Roughly 30 objects in the entire galaxy that we've been able to identify and confirm as magnetars. Now there are almost certainly more that we haven't spotted, because magnetars don't stay active forever, and a quiet one is very hard to find. But even generous estimates keep them extraordinarily uncommon compared to their ordinary cousins. Something about how these objects form, or how their fields develop, makes them the exception rather than the rule. Only a small fraction of neutron stars end up as magnetars, and figuring out exactly why is one of the open questions we'll come back to. Here's something that makes magnetars even more remarkable. They were dreamed up on paper before anyone ever confirmed one existed. In the early 1990s, a small number of theorists worked out that if a newborn neutron star spun fast enough at birth, it might generate a magnetic field far beyond anything ordinary neutron stars carried, and they gave this hypothetical object the name Magnetar. It was, at first, just a prediction, a piece of physics reasoning about what ought to be possible, but nature obliged. Over the following years, astronomers connected that prediction to real objects in the sky, strange sources that produced repeating bursts of gamma rays and glowed too brightly in X-rays to be powered by rotation alone. Piece by piece, the theoretical magnetar and these puzzling real sources were recognized as the same thing. It's a lovely example of how physics can anticipate reality, describing an object no one had yet confirmed, and then watching the universe reveal that such objects were out there all along, waiting to be understood. There's another important subtlety here, one that's easy to miss and that reshapes how we should think about these objects. When astronomers say a magnetar has a field of, say, 100 billion Tesla, what they're usually describing is the large-scale field, the smooth, overall magnetic structure measured from the outside, from the way the star's rotation slows down over time, or the way its light behaves. But there are strong reasons to think that this externally measured field is not the whole story. It may be only the calm outer face of something far more chaotic and powerful hidden beneath the surface. Think of it this way. When you look at the Earth's magnetic field from space, you see a relatively simple pattern, roughly like a bar magnet, with a north pole and a south pole and smooth field lines looping between them. But down inside the Earth, in the churning molten metal of the outer core, the actual magnetic field is a tangled, turbulent, constantly shifting mess. Far more complicated than the neat pattern we see from outside. The simple external field is just the large-scale average of all that hidden complexity. Something similar is very likely true for a magnetar, only far more extreme. The field we measure from outside may be the smooth surface expression of an internal field that is knotted, twisted, and locally even stronger, wound through the dense interior of the star in ways we cannot directly see. This matters enormously, and it's going to be central to everything that follows. Because if a magnetar's real magnetic strength is hidden inside it, tangled and stressed, and locally more intense than the field we measure from far away, then that hidden field is a reservoir. It's a vast store of energy, coiled up and held under tension inside the star, waiting. And unlike the energy of a normal star, which comes from fusion in the core, this energy has nothing to do with nuclear burning at all. The magnetar isn't fusing anything to power itself. Its violence, when it comes, is drawn from the magnetic field itself, from the enormous energy locked in that twisted internal structure. That's a genuinely different kind of engine than anything we usually think of when we picture a star. And it's the reason a magnetar can do what an ordinary neutron star cannot. Let me draw the distinction sharply, because it's one of the most important ideas we'll return to again and again. An ordinary star shines because of nuclear fusion, converting light elements into heavier ones and releasing energy in the process. A neutron star does not do this. It's a dead core, no longer fusing. Instead, a young neutron star shines mostly because it's still hot from its violent birth, slowly radiating away the leftover heat of its formation, and because it's spinning, converting some of that rotational energy into radiation. But a magnetar has a third and far larger reservoir available to it, one that ordinary neutron stars barely tap: the energy stored in its own colossal magnetic field. That magnetic energy is so vast that it can dominate everything else about the object. It can power a steady glow of X-rays for thousands of years. And when it's suddenly released, it can produce the violent eruptions that make magnetars famous. The magnetic field isn't just a property of the magnetar. It is the magnetar's true power source. To feel how strange that is, consider what it means for the object's lifetime. An ordinary young pulsar, a spinning neutron star, slowly winds down over millions of years as it radiates away its rotational energy, gradually spinning slower and glowing fainter. Its story is fundamentally a story about rotation. But a magnetar's story is fundamentally a story about magnetism. Its brightness, its bursts, its whole dramatic career are governed not by how fast it's spinning, but by how much magnetic energy it holds, and how that energy leaks out or erupts over time. Two objects that look superficially similar, both being spinning neutron stars, can live completely different lives depending on which energy reservoir dominates. For most neutron stars, rotation is the main story. For a magnetar, the magnetic field is the main story, and the difference is everything. Now, I want to be careful and honest here, because this is a field of active research and not everything is settled. We are quite confident that magnetars exist, that they are neutron stars, and that they carry the strongest magnetic fields directly associated with any known stellar object. That much is on very firm ground, supported by decades of observation. But when it comes to the details of the internal field, its exact geometry, how tangled it really is, how much stronger it is inside than outside, we are working from a mix of observation and theoretical modeling. We cannot cut a magnetar open and look. We infer what's inside from what we can measure outside, and from what the laws of physics tell us must be happening in matter that dense and fields that strong. So, when I describe the hidden internal field, I want you to hold it as our best, well-motivated picture, not as something anyone has directly seen. The distinction between what we observe and what we model is one we'll keep coming back to, because it's what honest science looks like at the edge of the known. But even with that caution in place, the core picture is remarkable and worth sitting with. We have an object left behind by the death of a massive star. It's the size of a city and heavier than the sun. It's so dense that a spoonful of it weighs as much as a mountain. It spins, though, as we'll see, often surprisingly slowly for reasons we'll unravel, and it's wrapped in and shot through with a magnetic field so powerful that it distorts atoms, reshapes the space around it, and stores an almost unfathomable amount of energy in its twisted internal structure. That field is not a side effect, it's the defining feature, the thing that separates a magnetar from the vast population of ordinary neutron stars and turns it into one of the most violently variable objects we know. Everything that we're going to explore from here builds on this foundation. We're going to ask where such an outrageous magnetic field comes from in the first place, and we'll find that even that question doesn't have a single settled answer, only competing ideas that scientists are still weighing against each other. We're going to look at how that field stores its energy, and why a magnetar can keep glowing long after the supernova that made it has faded from view. We're going to descend into the crust of the star and see how the evolving field stresses the solid outer shell until something has to give. We'll follow that stress out into the magnetosphere, the region of field and plasma surrounding the star, and watch the field lines wind tighter and tighter. And finally, we'll see what happens when all of that stored tension is suddenly released, when the magnetar erupts and briefly floods space with a burst of radiation so concentrated and so abrupt that in its instantaneous intensity, it can rival even the great explosions that create these objects in the first place. But for now, let this first idea settle in, because it's the anchor for all of it. A magnetar is a neutron star. It's the corpse of a giant star, packed into the size of a city, holding the mass of a sun. And it carries the strongest magnetic field directly tied to any stellar object we've ever found. A field that may be far more tangled and powerful inside than the smooth pattern we measure from the outside suggests. That hidden, coiled, tremendously energetic magnetic structure is the loaded spring at the heart of everything. It's the reason a dead star no bigger than a town can suddenly, without exploding, become one of the most violent objects in the universe. The question we have to answer next is how a newborn neutron star could ever come to possess such a monstrous field in the first place. And as we'll see, the answer is neither simple nor fully known. So we're left standing at a question, and it's a genuinely hard one. We have this object, a neutron star wrapped in a magnetic field 100 million times stronger than anything human hands have ever built. And the obvious thing to ask is simply, where did that field come from? A star doesn't just decide to become 100 billion times more magnetic than the machines in our laboratories. Something has to create that field, something has to concentrate it, and something has to lock it into the star and keep it there. And here's the honest truth that makes magnetars so fascinating to the people who study them. We don't fully know the answer. There isn't one clean, settled story. There are several competing ideas, each with real evidence behind it, and the actual origin of magnetar strength fields remains one of the open frontiers of the science. So let me walk you through the leading possibilities, not as a single tidy explanation, but as the genuine puzzle it is. The first idea, and probably the most famous, involves something called a dynamo. Now, a dynamo is not exotic. It's the same basic process that generates the magnetic field of the Earth, and of the Sun, and of countless other objects in the cosmos. The core idea is this: when you have an electrically conducting fluid that is moving, churning, and rotating all at once, that motion can generate and amplify a magnetic field. Moving charged material makes magnetic fields, and if the motion is organized in the right way, especially by rotation, it can take a weak seed field and pump energy into it, twisting and stretching and folding it until it becomes vastly stronger. Inside the Earth, molten metal churns in the outer core, and that churning sustains the magnetic field that shields our planet and points our compasses. It's a self-reinforcing engine, converting the energy of motion into magnetic energy. Now picture the birth of a neutron star in the first seconds of its existence. This is a moment of almost unimaginable violence and heat. The core of a massive star has just collapsed, crushing down into a ball of neutron matter, and in those first moments, the newborn neutron star is not the quiet, solid object it will eventually become. It is molten in a sense, seething, incredibly hot, with material convecting furiously, churning and rolling as the star tries to settle into its new state. If, during those first few seconds, the newborn neutron star is also spinning extremely fast, spinning perhaps hundreds of times every second, then you have exactly the ingredients a dynamo needs. You have a conducting fluid, you have violent churning motion, and you have rapid rotation to organize it all. Under those conditions, the theory goes, a dynamo could switch on and pump the magnetic field up to staggering strengths in just a few seconds, freezing an enormous field into the star before it cools and solidifies. That's the appeal of the dynamo idea. It offers a natural way to reach magnetar-level fields, and it makes a specific testable prediction. For the dynamo to work at full power, the newborn neutron star has to be spinning very, very fast at birth, faster than most neutron stars are thought to spin when they form. So the dynamo idea predicts that magnetars should come specifically from stars that leave behind extremely rapidly rotating cores. It's an elegant picture. The faster the newborn star spins, the more powerfully the dynamo runs, and the stronger the resulting field. And if this is right, then the most powerful magnetars are the children of the most rapidly spinning stellar cores. But there's a competing idea, and it's just as reasonable. This second idea is called fossil field, or inherited flux, and it works on a completely different principle. Instead of generating the field fresh at the moment of birth, this idea says the field was there all along, inherited from the original star. Here's the thinking. The massive star that eventually collapses already had a magnetic field of its own during its long life. Stars are magnetic. Even our own sun has a magnetic field, tangled and dynamic and responsible for sunspots and solar flares. Now, the magnetic field of a big star is spread out across an enormous volume. Because the star itself is huge, often larger than the orbit of the Earth around the sun. The field is weak in any given place, but it threads through a truly vast amount of space. Then the star dies, and its core collapses. And here's the crucial part. There's a principle in physics that, under the right conditions, magnetic field lines are effectively frozen into the conducting material they thread through. When that material collapses and shrinks, the field lines are dragged along with it, and they get concentrated. squeeze the material into a smaller and smaller volume, and the field lines are squeezed right along with it, packed closer and closer together, which means the field gets stronger and stronger. It's a bit like taking a loosely woven net spread across a football field and gathering it up into a tiny, tightly bunched knot in your fist. The threads that were spread thin across a huge area are now crammed into a tiny space, and their density skyrockets. In the same way, a modest magnetic field threading the core of a giant star, when that core collapses down to a city-sized neutron star, could, in principle, be concentrated to enormous strength. The appeal here is different from the dynamo. This idea doesn't require the newborn star to spin at some special breakneck rate. It just requires the original star to have had a reasonably strong, well-organized magnetic field to begin with, one that then gets concentrated by the sheer geometry of collapse. And there's a natural way for some massive stars to acquire unusually strong fields during their lives, perhaps through mergers with companion stars, or through their own internal dynamos operating over their long lifetimes. If a star ends its life with a particularly strong, ordered magnetic field, then even ordinary collapse could concentrate that field into Magnetar territory. Under this picture, Magnetars are simply the remnants of the most strongly magnetized massive stars, and the field they carry is a fossil, a preserved and compressed memory of the field their parent star already had. So which is it? Dynamo, generating the field fresh from rapid rotation at birth? Or fossil field, inheriting and concentrating a field that already existed? And the honest, important answer is that we're not certain, and it may not be a strict either or. It's entirely possible that both processes contribute, that different magnetars are made in different ways, or that some combination of inherited field and dynamo amplification is at work. Nature is rarely obligated to pick just one mechanism. There are also other subtler pathways that researchers explore, involving the details of how the collapsing core rotates and convects, how instabilities develop in those first violent seconds, and how the field organizes itself as the star settles. The point I most want you to take away is this: the extreme magnetic field of a magnetar is real and measured, but the story of its origin is still being written. Anyone who tells you there is one proven mechanism that explains every magnetar is overstating what we actually know. This is a live scientific question, and that uncertainty is not a weakness of the science. It's the frontier of it. Now, how do astronomers actually weigh these competing ideas against each other if they can't see the field being born? They look for clues in the surroundings and the histories of magnetars, and this detective work is genuinely fascinating. One approach is to study the supernova remnants that magnetars are found inside. When a magnetar is discovered sitting at the heart of an expanding cloud of debris, that cloud is the wreckage of the very explosion that created it. By studying the remnant, astronomers can estimate how long ago the explosion happened, and sometimes even glean hints about the star that died. This lets them ask, are magnetars young, freshly made objects? And the answer is yes. The magnetars we find tend to be young, often just thousands of years old, exactly as we'd expect for objects whose extreme fields are still active and haven't yet decayed away. A second approach is to work out what kind of star each magnetar came from. Every neutron star is the corpse of a specific massive star, and by studying the environment and the remnant, astronomers can sometimes estimate how massive that original star must have been. If magnetars came only from a very specific, narrow range of extremely massive stars, that would point one way. If they came from a broader range, that would point another. The evidence here is still being gathered and debated, and it hasn't cleanly settled the dynamo versus fossil field question. But each magnetar studied adds another data point to the puzzle, another constraint on which formation stories are allowed and which are ruled out. But perhaps the most revealing clue of all comes from a strange subclass of objects that, at first glance, shouldn't exist. Remember that we identify magnetars largely by their enormous magnetic fields, measured from how quickly they slow down. Well, astronomers have found a handful of neutron stars whose externally measured fields are surprisingly modest, no stronger than many ordinary pulsars. And yet, these objects behave like magnetars. They produce the bursts, they flare. They do the violent things only magnetars are supposed to do, despite their measured field being unremarkable. These are sometimes called low-field magnetars, and they present a puzzle that turns out to be deeply illuminating. How can an object with an ordinary-looking external field erupt like a magnetar? The leading explanation circles right back to the idea we've been developing. The field we measure from the outside is not the whole story. These objects may carry a hidden internal field far stronger than their smooth external field suggests. A tangled, powerful field locked inside the star and inside the crust, capable of driving eruptions even though the large-scale field measured from far away looks tame. In other words, these low-field magnetars may be direct evidence that the internal field can dominate the external one, that a neutron star's true magnetic character can be hidden beneath a deceptively quiet surface. If that interpretation holds, then the very existence of these objects supports the picture that a magnetar's real power lives inside it. In a reservoir we cannot measure directly, only infer from the violence it produces. It's a beautiful case of an apparent contradiction, magnetar behavior without a magnetar strength external field, actually strengthening our understanding rather than undermining it. But let's set the origin question aside for a moment, because whatever created the field, once it exists, it becomes the beating heart of the object. And this brings us to what may be the single most important concept for understanding magnetars at all. The difference between a magnetar's energy and the energy of ordinary stars. When you think about where a star gets its power, you naturally think of nuclear fusion. The sun shines because deep in its core, hydrogen nuclei are being fused into helium, releasing energy that works its way out and pours into space as sunlight. That's the engine of a normal star, and it's a nuclear engine. But a magnetar does not run on fusion. It's a dead core. It stopped fusing long ago in the collapse that created it. So when a magnetar glows, when it bursts, when it erupts, that energy is not coming from nuclear burning. It's coming from somewhere else entirely. It's coming from the magnetic field itself. This is a genuinely different kind of engine, and it's worth slowing down to appreciate it. A magnetic field is not just a passive property, like a color or a label. A magnetic field contains energy. It takes energy to create a magnetic field, and that energy is stored in the field, held in the very structure of it, in the way the field lines are arranged and threaded through space. The stronger the field, the more energy it holds. And a magnetar's field is so outrageously strong that the energy stored in it is colossal, far exceeding the everyday energies we're used to thinking about. That stored magnetic energy is a reservoir, an enormous tank of energy locked into the object, distinct from its heat, distinct from its rotation, distinct from anything left over from the original supernova. And crucially, that reservoir can be tapped. Over time, and sometimes suddenly, the magnetic field can release its stored energy. This process is often called field decay. The idea is that the magnetic field of a magnetar is not perfectly stable and eternal. It evolves. It slowly rearranges itself. It decays, and as it decays, it releases energy. And that released magnetic energy has to go somewhere. Much of it turns into heat, warming the star, and into radiation, streaming out into space. This is the key to one of the most striking features of magnetars. They can shine steadily and persistently in X-rays for thousands of years after the supernova that created them has completely faded from view. Let me make sure that lands, because it's a beautiful and slightly counterintuitive idea. When a massive star explodes as a supernova, the explosion itself is dazzlingly bright for a few weeks or months, and then it fades. The expanding cloud of debris glows for a while longer, for thousands of years, as a supernova remnant, but the light of the explosion itself is long gone. So what powers a neutron star's glow after all that time? For an ordinary neutron star, the answer is mostly leftover heat, slowly radiating away, growing fainter and fainter over the ages. But a magnetar has an extra, much larger power source available. As its magnetic field slowly decays, it deposits energy into the star, keeping it hot, keeping it glowing in X-rays far more brightly than leftover birth heat alone could ever manage. The magnetar is being warmed from within, not by nuclear fire and not merely by fading birth heat, but by the gradual unwinding of its own magnetic field. It's as if the object carries a slow-burning battery, and that battery is the magnetic field itself, discharging its stored energy across the centuries. This is why magnetars can be detected as persistent, luminous X-ray sources. The magnetic field is constantly, quietly leaking energy, and that leak keeps the surface hot enough to shine in high-energy light. The steady glow we observe is, in a real sense, the sound of the magnetic field slowly coming undone. And that same process, the decay and rearrangement of the field, is the thing that, in more sudden and violent forms, will eventually produce the bursts and flares we'll come to later. The persistent glow and the sudden eruption are two faces of the same underlying reality. A magnetic field so strong that its very existence is a store of energy, and its gradual or sudden release is what we see as light. Now, I want to turn to a puzzle that, when you first hear it, sounds almost like a contradiction, but which actually reveals something deep about how magnetars work. You'd expect a young neutron star to be spinning extremely fast, and many are. When a massive stellar core collapses, it spins up dramatically, for the same reason a figure skater spins faster when she pulls in her arms. As the core shrinks from something larger than the Earth down to a ball 20 kilometers across, its rotation accelerates enormously. Ordinary young neutron stars, the pulsars, often spin many dozens of times every second, whipping around blazingly fast. So here's the puzzle. Magnetars, despite being young and compact, often rotate surprisingly slowly. A typical magnetar might take several seconds to complete a single rotation. Compare that to an ordinary young pulsar spinning around dozens of times a second, and the magnetar seems almost sluggish. How can an object that should have been born spinning fast end up turning so slowly? The answer is one of the most elegant consequences of that enormous magnetic field, and it's called magnetic braking. Here's how it works. A spinning magnetized object doesn't just sit there quietly. It drags its magnetic field around with it as it rotates, and that spinning magnetic field flings out energy and charged particles into space, radiating away energy and carrying off some of the star's rotational momentum with it. Every neutron star does this to some degree, which is why even ordinary pulsars gradually slow down over millions of years. But the rate at which a star loses its spin depends dramatically on the strength of its magnetic field. A stronger field acts like a more powerful brake. It flings out energy far more aggressively, and so it drains rotational energy far more quickly. And a magnetar's field is not just a little stronger, it's 100, 1,000 times stronger than an ordinary neutron star's. So the braking effect is correspondingly ferocious. Where an ordinary pulsar might take millions of years to noticeably slow down, a magnetar's colossal field acts as such a powerful brake that it bleeds away the star's rotation with astonishing speed, in astronomical terms. Even if a magnetar is born spinning rapidly, its own monstrous magnetic field slams on the brakes so hard that within a few thousand years, the star has been slowed down to a rotation of once every several seconds. The very field that makes the Magnetar so violent is also the thing that saps its spin. The stronger the field, the harder the brake, and the more quickly the star loses its rotation. This leads us to a conclusion that reshapes how we think about the object entirely, and it circles back to the theme we introduced earlier. For an ordinary pulsar, rotation is the main energy reservoir. It's a spinning top, slowly winding down, and its light and its behavior are governed by that dwindling spin. But for a magnetar, rotation is almost beside the point. The magnetar has slowed down so much, so quickly, that its rotational energy is relatively modest. The dominant reservoir, the thing that actually powers the magnetar's dramatic career, is not its spin at all. It's the magnetic field. The magnetic energy stored in a magnetar utterly dwarfs the energy left in its slow rotation. And that's why we say the magnetar's most important energy reservoir is not necessarily its current rotation, it's the field. Let me draw this distinction as sharply as I can, because it's central to everything. We now have in play 4 completely different kinds of energy, and keeping them straight is essential to understanding these objects honestly. First, there's the energy of the original supernova, the titanic explosion that created the neutron star in the first place. That energy was released long ago in the birth event, and it's gone, dispersed into the expanding cloud of debris. Second, there's thermal energy, the leftover heat of the star's violent formation slowly radiating away over time. Third, there's rotational energy, the energy of the star's spin, which magnetic braking drains rapidly in the case of a magnetar. And fourth, there's magnetic energy, the vast store of power locked into the magnetic field itself. For an ordinary pulsar, rotational energy is the star of the show. For a magnetar, magnetic energy dominates everything. These are genuinely separate reservoirs, filled at different times and drained by different processes, and it's easy to blur them together into one vague notion of the star's power. But they're not the same. And the whole character of a magnetar comes from the fact that, for it, the magnetic reservoir is the deepest and most important one of all. There's a wonderful subtlety hiding in the magnetic braking story too, and it ties back to the uncertainty about the internal field. When astronomers measure how quickly a magnetar is slowing down, they can actually use that measurement to estimate the strength of its magnetic field. A faster slowdown implies a stronger break, which implies a stronger field. This is, in fact, one of the main ways we infer that magnetars have such enormous fields in the first place. We watch how fast they lose their spin, and we work backward to the field strength that must be causing it. But, and here's the subtlety, this measurement tells us about the large-scale field, the smooth overall structure that does the breaking. It doesn't directly reveal the tangled, potentially much stronger field hidden inside the star. So once again, we find ourselves distinguishing what we observe, the slowdown and the large-scale field we infer from it, from what we model, the twisted internal field that theory tells us is likely there, but that we cannot measure directly. The breaking gives us a real, solid handle on the external field. The interior remains, to a significant degree, a matter of well-motivated inference. And it's precisely that interior, that hidden reservoir of a tangled magnetic energy, that sets the stage for everything violent that magnetars do. Because a magnetic field this strong, wound through matter this dense, is not a comfortable, relaxed arrangement. It's a field under enormous internal stress, held in a configuration it would rather escape from, coiled and knotted and pushing against the material that contains it. The persistent X-ray glow we talked about is the gentle, continuous version of that field releasing its energy, a slow leak. But a field under that much stress does not always leak gently. Sometimes it moves suddenly. Sometimes the stress builds until something gives way, and when it does, the release is not a leak, but an eruption. To understand how that happens, we have to look at where the internal field meets the solid outer shell of the star, at the crust of the magnetar, and at how the relentless pressure of the evolving field builds up against it. Because the field does not exist in isolation. It's embedded in matter, threaded through the crust and the ultra-dense interior, and as the field evolves and tries to rearrange itself into a lower energy configuration, it drags on that matter, stresses it, and strains it. The magnetic energy we've been discussing, that vast reservoir, is coupled directly to the physical structure of the star. And the story of a magnetar's violence is, at its core, the story of that coupling reaching a breaking point. So let me gather the thread before we descended to the crust. We began with a question we couldn't fully answer. Where does a magnetar's field come from? And we found not one answer, but several. A dynamo generating the field fresh from rapid rotation at birth, a fossil field inherited and concentrated from the parent star, and other pathways besides, with the genuine origin still unsettled and quite possibly varying from one magnetar to the next. Whatever the origin, once the field exists, it becomes the object's dominant reality. It stores an enormous reservoir of energy that has nothing to do with the nuclear burning. As that field slowly decays, it powers a persistent X-ray glow that outlasts the fading supernova by thousands of years, warming the star from within. That same colossal field breaks the star's rotation so hard that magnetars, despite being young, spin surprisingly slowly, having shed their spin in a geological eye blink. And this leaves the magnetic field, not the rotation, as the true and dominant energy reservoir, distinct from the star's heat, its spin, and the long-vanished energy of its birth explosion. That reservoir is loaded. It's coiled with stress, embedded in dense matter, pushing against the crust that contains it. And a loaded reservoir under enough stress does not stay quiet forever. The next step in our story is to go down to the surface, into the crust of the Magnetar and see exactly how the pressure of that hidden field builds against the solid shell of the star, until the moment when the crust can no longer hold, and the Magnetar is pushed toward the violent release that makes it one of the most extraordinary objects in the universe. Now we go down to the surface, because this is where the invisible drama of the magnetic field becomes a physical, mechanical struggle against solid matter. And to understand that struggle, we first have to understand what the surface of a magnetar actually is. Because it's nothing like the surface of any object you've ever touched or imagined. A neutron star, and therefore a magnetar, has a crust. That word might make you picture something like the crust of the Earth. A shell of rock over a molten interior, and in the broadest structural sense, that analogy has a grain of truth. There's a solid outer layer over a stranger interior, but the resemblance ends almost immediately, because the material of a magnetar's crust is unlike anything in ordinary experience. It's not rock. It's not metal in the sense you know. It's matter crushed to densities so extreme that our everyday intuitions about solids simply don't apply. Let me build the picture from the outside in. At the very outermost skin of the star, the density is already enormous by ordinary standards, but as you go deeper, it climbs relentlessly. Just a short distance beneath the surface, the matter is packed so tightly that atomic nuclei are jammed together into a rigid, crystalline arrangement, a lattice held in place by the crushing pressure and by the intense electrical forces between the nuclei. This is the crust. A solid, crystalline shell, but a crystal made of material so dense that a sugar cube-sized piece of it would weigh as much as an entire mountain. It's often described as being incredibly rigid, far more rigid than any steel, because the forces locking that lattice together are so overwhelmingly strong. The crust of a magnetar may be, by some measures, the strongest solid material anywhere in the universe, and beneath that crust, things get stranger still. As you descend deeper, the density rises until the very nuclei that make up the lattice begin to dissolve, their neutrons leaking out and flooding the spaces between them. Deeper yet, you reach the interior proper, the vast bulk of the star, where matter is thought to become a bizarre fluid of neutrons, possibly behaving as a superfluid, a frictionless liquid with properties that have no counterpart in daily life. And at the very center, in the deepest core, the state of matter becomes genuinely uncertain, so extreme that physicists are not sure exactly what form it takes. That fluid interior deserves a closer look, because it plays a quiet but important role in the drama to come. The vast bulk of a neutron star beneath the crust is thought to be a superfluid, and a superfluid is a genuinely strange state of matter. A liquid that flows with absolutely no friction, no resistance, no drag. On Earth, we can coax certain substances into superfluid states only at temperatures near absolute zero. And even then, they behave in ways that seem to defy common sense. Climbing walls, flowing through impossibly tiny gaps. Inside a neutron star, an ocean of neutrons is believed to exist in just such a frictionless state, filling the interior beneath the rigid crust. Here's why that matters for our story. You have a frictionless superfluid interior, and above it, a solid, rigid crust. These two components are not perfectly locked together. The superfluid inside can, in a sense, rotate somewhat independently of the crust, decoupled from it by its own frictionlessness. And this separation sets up a subtle tension between the interior and the crust. a mismatch that can build over time. When the crust suddenly shifts or fails in a starquake, part of what's happening is a sudden readjustment in how the crust and the superfluid interior are coupled, a jolt that can momentarily change the star's rotation. This is why some bursts are accompanied by tiny, sudden jumps in the Magnetar's spin. Those spin changes are in effect the mechanical fingerprints of a starquake, evidence written into the star's rotation that something abrupt happened deep in the coupling between the crust and the strange, frictionless ocean beneath it. So the structure roughly is this: a solid crystalline crust, incredibly rigid and incredibly dense, sitting atop a deep interior of exotic, ultra-dense fluid matter, and the magnetic field threads through all of it, crust and interior alike, woven into the very fabric of the star. I want to be careful with the language here, because it's easy to slip into a misleading picture. It's tempting to imagine the crust as behaving like ordinary brittle rock, something that snaps cleanly like a dropped plate, and sometimes that image is used as a rough shorthand. But the reality is more subtle, and the subtlety matters. The crust is under conditions so extreme, such immense pressure, such incredible density, that its behavior is not simply that of familiar brittle stone. Under some conditions it may indeed fail suddenly, cracking or fracturing, but under other conditions it may deform more gradually, flowing or yielding slowly, shifting under stress rather than shattering. The precise way the crust responds to force is itself an area of active study, and it depends on details we're still working out. So I'll avoid telling you flatly that the crust cracks like rock, because that would be claiming more certainty than we have. What we can say confidently is that the crust is solid, tremendously strong, and capable of failing, yielding, or shifting when the stress on it grows too great. Exactly how it fails may vary, and that's part of the honest picture. Now, why would the crust ever be stressed in the first place? Here we return to the magnetic field and to the central mechanism of the entire Magnetar story. Remember that a Magnetar's field is not a calm, stable, relaxed thing. It's a field of monstrous strength, wound through the dense interior of the star, and it's under enormous internal stress. It's held in a configuration it would rather escape from, coiled and knotted, pushing and pulling against the matter that contains it. And crucially, that field is not frozen forever. It evolves. Over time, the internal magnetic field slowly shifts and rearranges itself, driven by its own tension, trying to find a lower energy, more relaxed configuration, the way a twisted rubber band strains to unwind. But here's the thing. The field is embedded in matter. It's threaded through the fluid interior and locked into the rigid crust. So when the internal field tries to move and rearrange itself, it can't do so freely, because it's bound up with the material of the star. As the deep internal field evolves, it pulls and pushes on the crust from below and within, transmitting its stress directly into that rigid crystalline shell. The magnetic field, in effect, grabs hold of the crust and strains it, exerting forces that build up gradually over time. The evolving field places enormous, mounting stress on the crust, and the crust, being solid and rigid, resists. It holds, it holds, it holds, but nothing holds forever. The stress builds and builds, and as the internal field continues to evolve and drag on the crust, the strain accumulates until it approaches the limit of what the crust can bear. And when the magnetic stress finally exceeds what the crust can support, something has to give. The crust yields. It may crack, it may fracture, it may shift, It may deform depending on the local conditions, but in some way it fails, suddenly releasing the strain that had been building. And this event, this sudden yielding or shifting of the magnetar's crust under magnetic stress, is what astronomers call a starquake. The word is perfect, because it's genuinely the neutron star equivalent of an earthquake. On Earth, tectonic stresses build up along fault lines over years and decades, the rigid crust holding against the strain until, in a sudden, violent moment, it slips, and that sudden slip is an earthquake, releasing all the accumulated energy at once. On a magnetar, the driving force is different. It's magnetic stress rather than tectonic motion, but the essential drama is the same. Stress accumulates in a rigid crust until the crust can no longer hold, and then, suddenly, it gives way, releasing energy in a violent event. A starquake. But a starquake on a magnetar is far more consequential than any earthquake on Earth. And to understand why, we have to follow what happens when the crust moves. Here is the key link in the entire causal chain. The connection that turns a mechanical event on the star's surface into a burst of radiation flooding across the galaxy. When the crust of a magnetar shifts or cracks or fails, it doesn't just release mechanical energy locally. Remember that the magnetic field is anchored in the crust. Its field lines rooted in the crystalline surface like the roots of trees anchored in soil. So when the crust moves, it drags the roots of the magnetic field with it. A sudden shift in the crust suddenly displaces the footpoints of the magnetic field, jerking and twisting the field lines that are attached to the surface. And because those field lines extend far up and out from the star into the surrounding space, a disturbance at their roots propagates outward, disturbing the entire external magnetic structure. This is how a physical event inside or on the surface of the star reaches out and disturbs the field far above it. The crust and the field are coupled. Move one, and you move the other. A starquake at the surface sends a disturbance racing up the magnetic field lines, out into the region surrounding the star, and it's out there, in that region, that much of the real violence unfolds. So we have to shift our attention now from the solid crust to the space just above it, to the vast magnetic structure that surrounds the magnetar, the region we call the magnetosphere. The magnetosphere is the region of space around the star that's dominated by the magnetic field. It's not empty. It's threaded through with the magnetar's colossal field, and it's populated with charged particles, with plasma, electrically charged material that's caught up in the field and forced to move along it. Charged particles cannot easily cross magnetic field lines. Instead, they're channeled along them, spiraling around them, trapped and guided by the magnetic structure. So the magnetosphere is a dynamic arena of field and plasma, tightly coupled together, the plasma constrained by the field, and the field shaped, in turn, by the currents the plasma carries. It's the outer kingdom of the magnetar, the realm where the field reaches out from the star into the surrounding void. And in a magnetar, this magnetosphere is not in a simple, relaxed state, it's twisted. Here's why that matters so much. When the internal field evolves, and the crust shifts, and the footpoints of the field lines are dragged around by the moving crust, the field lines above the surface get twisted up. Imagine grabbing the base of a bundle of threads and giving it a sharp twist while the tops stay fixed. The whole bundle winds up, coiling around itself, storing tension in the twist. Something similar happens to the magnetic field lines of a magnetar. As the crust shifts and the foot points move, the field lines threading out through the magnetosphere become sheared and twisted, wound up into a stressed, contorted configuration. And a twisted magnetic field, like a twisted spring or a wound-up rubber band, stores additional energy. This is a crucial point. The twisting doesn't just deform the field, it pumps energy into it, loading it with tension. The more the field is twisted, the more energy is stored in that twist, held in the magnetosphere, waiting. So now we have energy accumulating not only inside the star, in the internal field, but also outside it, in the twisted magnetosphere, sheared and stressed by the motions of the crust below. The whole system, star and surrounding field alike, is being loaded with magnetic tension, wound tighter and tighter over time. I want to pause and resist a tempting but misleading image, because it's important to get this right. It's very natural to picture magnetic field lines as physical ropes or strands, actual threads you could grab and twist and tie in knots. And the language of twisting and shearing and foot points practically invites that picture. But magnetic field lines are not physical objects. They're not ropes or wires or strings. They're a way of representing the shape and direction of the magnetic field, a map of where the field points and how strong it is at each place in space. When I say the field lines get twisted, I'm using a vivid shorthand for a real physical fact, that the magnetic field itself takes on a sheared, contorted configuration, and that this configuration stores energy. But there's no actual rope up there being tied in a knot. There's a field, an invisible influence filling space, and it's the arrangement of that field, its geometry, that's being stressed and loaded with energy. Hold on to the intuition the rope image gives you. That twisting stores tension and energy, but don't mistake the metaphor for the reality. The field is not made of strands. It's a smooth, invisible structure whose shape carries energy. With that clear, let's see where all this tension is heading, because a system loaded with more and more stored energy is a system heading toward release. Inside the star, the internal field strains against the crust. Outside the star, the twisted magnetosphere holds energy in its sheared configuration, and both are building toward a moment when the accumulated stress can no longer be contained, when the field, inside or outside or both, suddenly rearranges itself into a lower energy state, dumping its stored energy all at once. This sudden rearrangement is the trigger of a Magnetar's eruption, and it likely involves a process called magnetic reconnection, along with the abrupt reconfiguration of the stressed field. Let me explain reconnection carefully, because it's one of the most important processes in all of high-energy astrophysics, and it's happening in gentler forms even on our own sun, where it powers solar flares. When a magnetic field is twisted and stressed into a contorted configuration, it's in a high-energy state, holding tension it would rather release. Under the right conditions, the field can suddenly find a shortcut to a lower energy arrangement. The stressed field lines, in effect, snap into a new, simpler configuration, and in doing so, they release the energy that had been stored in the twist. This sudden reorganization of the magnetic field, this snapping from a stressed high-energy geometry to a relaxed, lower-energy one, is reconnection, and it can happen explosively fast. And when it happens, the released energy has to go somewhere. It pours into the plasma, the charged particles caught up in the field. The sudden magnetic reconfiguration accelerates those particles violently, hurling them to enormous energies, whipping them along the field at tremendous speeds. And accelerated charged particles radiate. They pour out energy as light, and given the enormous energies involved, that light is not gentle visible light, but high-energy radiation. X-rays and gamma rays, the most energetic forms of light there are. So the chain completes itself. Stored magnetic energy, released by sudden reconfiguration and reconnection, dumped into charged particles, accelerating them, and those particles blazing forth in a burst of intense high-energy radiation. That's the eruption. That's how the invisible tension in the field becomes a flash of light that can cross the galaxy. But I have to add a crucial and honest caveat, one that runs through this entire part of the story. While this overall picture, stress building in the field, the crust yielding, the field reconfiguring, particles accelerating, radiation pouring out, is well motivated and widely discussed, the exact trigger and precise sequence of a Magnetar eruption are still not fully understood. There are genuine open questions. Does a burst begin with a crust failure that then disturbs the field? Or does an instability in the magnetosphere itself begin the process, which then stresses the crust? Is the crucial event a sudden crack, or a more gradual yielding that reaches a tipping point? How exactly does the reconnection unfold, and what determines whether a given event is a small flicker or a catastrophic flare? These are questions researchers are actively working on, using observations and theoretical models and computer simulations to try to piece together the real sequence of events. So I want to be scrupulous about what we know and what we're modeling. We observe directly that magnetars produce sudden bursts of X-rays and gamma rays. That's a solid, measured fact. We observe that these bursts sometimes coincide with sudden changes in the star's rotation, hints that something mechanical happened at the surface. Those are observations. But the detailed internal story, the picture of the crust yielding and the field reconnecting, and the precise order in which it all happens, that's a model. A theoretical reconstruction built to explain what we see. Well supported and reasonable, but not directly witnessed. We cannot watch the crust of a Magnetar shift. We cannot see the field lines reconnect. We infer these things from the light that reaches us and from our understanding of the physics involved. And there is genuine, active debate about the details. The crust-yielding picture and the magnetosphere instability picture are not settled into one final universal answer, presenting either as the single proven trigger for every event would be claiming more than we know. The honest statement is that we have a compelling framework with real uncertainties still inside it. Let me hold both of those things together, because that balance is exactly what makes this science trustworthy. On one hand, we have a genuinely powerful and coherent picture. An ultra-strong internal field evolves and twists. Magnetic stress builds inside the star and its crust. The crust yields, or the magnetosphere becomes unstable. The field rapidly reconfigures, particles and trapped plasma are accelerated, and an intense burst of high-energy radiation pours out. That chain hangs together beautifully, each link connecting to the next, and it explains a great deal of what we observe. On the other hand, the fine details which link fails first, exactly how the crust behaves, precisely how the reconnection proceeds, remain genuinely uncertain and under investigation. Both statements are true at once. We understand the broad mechanism well. We do not yet understand every step in complete detail. And that's not a flaw in the story. It's the frontier of an active field of research, where the shape of the answer is clear, but the last details are still being filled in. There's something I find genuinely striking about this whole picture, and it's worth dwelling on before we move to the eruption itself. Everything violent that a magnetar does traces back, ultimately, to that hidden internal field we discussed earlier. The tangled, stressed magnetic structure locked inside the star, the persistent glow, the building stress, the starquakes, the twisted magnetosphere, the reconnection, the bursts, all of it flows from the field trying over time to rearrange itself into a lower energy state, and being unable to do so smoothly because it's bound up with the matter of the star. The magnetar is, in a sense, a battle between a colossal magnetic field that wants to relax and a rigid crust that refuses to let it. The field strains, the crust holds, the tension builds, and every so often the crust gives a little, or the field finds a shortcut, and a pulse of that pent-up energy escapes. The whole violent life of a magnetar is the slow, stuttering, sometimes explosive resolution of that battle. And notice how the crust and the field are utterly inseparable in this story. You cannot understand the eruption by looking at the crust alone or at the field alone. It's the coupling between them that matters. The field stresses the crust anchors the field. The crust's motion twists the field. The twisted field stores energy. The energy releases and reaches back to accelerate particles. Star and magnetosphere, solid matter and invisible field are locked together in a single connected system, and the burst is what happens when that whole coupled system reaches its breaking point and rearranges itself all at once. This is why, throughout our whole exploration, I keep returning to the same continuous chain rather than treating these as separate facts. They're not separate. They're one causal sequence, running from the deep interior of the star all the way out to the light that reaches our telescopes. Let me also connect this back to the energy reservoirs we so carefully distinguished before, because it's important to keep them straight even here in the thick of the mechanism. The energy released in a starquake and the subsequent burst is fundamentally magnetic energy. It's not nuclear energy, there's no fusion happening. It's not primarily rotational energy, though a starquake can cause a tiny sudden change in the star's spin as the crust shifts. It's not leftover heat from the birth of the star. It's the energy that was stored in the stressed, twisted magnetic field inside the star and in the magnetosphere above it, now suddenly liberated. The magnetic reservoir, the deepest and largest of the magnetar's energy stores, is being tapped, and tapped violently. When we watch a magnetar burst, we are watching the magnetic field pay out some of the vast energy it has been holding. Energy that ultimately traces all the way back to whatever process, dynamo or fossil field, or both, first wound that field to such monstrous strength at the star's birth. So let me draw together the thread of this descent, because we've travelled a long way, from the invisible field down into the solid crust and back out into the twisted magnetosphere. We found that the crust of a magnetar is a solid, crystalline shell of unimaginably dense matter, tremendously rigid, sitting over an exotic fluid interior, with the magnetic field woven through all of it. We saw that the evolving internal field, straining to rearrange itself, places mounting stress on that rigid crust, but cannot move freely because it's bound up with the star's matter. We watch the stress build until the crust yields, cracks, or shifts in a starquake. Being careful to note that the crust doesn't necessarily behave like simple, brittle rock, and that the exact manner of failure is still being studied. We followed the crucial link by which a disturbance at the surface, dragging the rooted field lines, propagates out and disturbs the entire external magnetic structure. We entered the magnetosphere, that arena of field and plasma surrounding the star, and saw its field lines twisted and sheared by the crust's motion, storing additional energy in the twist, while resisting the false picture of field lines as literal ropes. And we arrived at the trigger. Sudden magnetic reconfiguration and reconnection, snapping the stressed field into a lower energy state, accelerating particles and pouring out intense high-energy radiation, while acknowledging honestly that the exact trigger and precise sequence remain genuine, open questions. What we have at the end of this descent is a system loaded to the point of release. The internal field strains against the crust. The crust holds until it can't. The magnetosphere twists and stores energy, and the whole coupled structure stands poised on the edge of a sudden, violent rearrangement. All the tension we've been building, the stress accumulating in the crust, the energy loading into the twisted field, is now ready to be paid out in light. In the smallest events, that release is a mere flicker, a modest burst, but in the rarest and most extreme events, the release is something almost beyond imagining. A giant flare, an eruption so sudden and so intense that, for a fraction of a second, this dead star the size of a city can rival the great explosions that gave it birth. What that eruption actually looks like, how it unfolds moment by moment, how it can reach across the galaxy to touch instruments here on Earth, and in what precise and carefully bounded sense it can be called more violent than a supernova, is where our story reaches its climax. So now we arrive at the moment everything has been building toward, the release. We've followed the magnetic field from its mysterious origin, through its role as the star's dominant energy reservoir, down into the crust where its stress accumulates, and out into the twisted magnetosphere where energy loads into the sheared field. And we've left the system poised on the edge, loaded to the breaking point, ready to pay out its stored energy and light. Now let's watch what happens when it does, and let's build up carefully, because not all Magnetar eruptions are the same. In fact, the range is enormous, spanning from gentle flickers to the most violent electromagnetic events we've ever recorded from a stellar object. Let me lay out the full range, from quietest to most extreme, because understanding this spectrum is essential to understanding what a giant flare really is, and to avoiding the trap of thinking every Magnetar is constantly erupting in catastrophic explosions. There are roughly 4 levels of Magnetar activity, and they differ by staggering amounts. At the quietest level is the persistent emission we discussed earlier, the steady X-ray glow. This isn't an eruption at all, it's the continuous background hum of the Magnetar, powered by the slow decay of the magnetic field warming the star from within. Even a Magnetar just sitting quietly, not bursting, shines as a persistent X-ray source day after day, year after year. That's the baseline, the resting state. Above that baseline sit the short bursts, and these are the bread and butter of Magnetar activity, the most common eruptions by far. A short burst is a sudden spike of X-rays or soft gamma rays, lasting typically a fraction of a second, a brief, sharp flash, and then back to baseline. These are the events that first drew attention to this class of object, sudden repeating flashes from the same point in the sky. They're energetic, far more so than anything gentle, but on the scale of Magnetar violence, they're modest. The small stuff. A Magnetar might produce many of these, sometimes in flurries, dozens or hundreds crackling off over hours or days during an active period, then falling silent again for years. Most of what magnetars do most of the time is produce these short bursts. They're the ordinary weather of a magnetar's life. Above the short bursts come the intermediate flares, rarer and more powerful, lasting perhaps a second or more and releasing considerably more energy than a typical short burst. These are a step up, less frequent, more dramatic, but still not the top of the ladder. And then, at the very top, rarest and most violent of all, are the giant flares. These are the monsters, the events that make magnetars legendary. A giant flare releases in a fraction of a second an amount of energy that dwarfs the short bursts by factors of thousands or more. It's an eruption on a completely different scale, so rare that in all our decades of observation, we've recorded only a small handful of them across the entire galaxy and its neighbours. Giant flares are the exception even among magnetars, the once-in-a-generation cataclysms of these already extreme objects. I want to stress this rarity because it's easy to come away with a distorted picture. Most magnetar bursts are the small, short ones. The giant flares are extraordinarily uncommon. And here's an important and honest point. Not every magnetar has been observed producing a giant flare. In fact, the vast majority of known magnetars have never been seen to produce one at all. Giant flares have been confidently recorded from only a very small number of sources. So we should not imagine that every magnetar is a ticking bomb guaranteed to unleash a giant flare. Some may, over their lifetimes, many may never do so, or may do so rarely that we've simply never caught them in the act. The giant flare is the most spectacular thing a magnetar can do, but it's also among the rarest, and it would be wrong to treat it as the typical behaviour of these objects. Most magnetars, most of the time, are either glowing quietly or producing modest, short bursts. The giant flare is the rare, violent exception. But oh, what an exception it is. So let's look closely at the anatomy of a giant flare, because it has a distinct and revealing structure. A structure that tells us directly about the physics unfolding on and around the star. A giant flare, when it happens, unfolds in a characteristic sequence, and that sequence comes in essentially 3 acts. The first act is the initial spike, and it's almost incomprehensibly brief and brilliant. In a fraction of a second, a tiny sliver of time, the magnetar releases an enormous pulse of the hardest, highest energy radiation. A spike of gamma rays and X-rays so intense that it can briefly outshine everything. This initial spike is where most of the flare's energy comes out, and it comes out almost instantaneously. Think about that. The vast bulk of the energy of one of the most violent events in the galaxy is dumped out in less time than it takes you to blink. This is the abruptness that defines a giant flare. The near instantaneous release of a colossal amount of energy. It's this spike, this sudden violent pulse, that gives the giant flare its almost unbelievable, instantaneous intensity. The second act is the intense release of X-rays and gamma rays that accompanies and immediately follows that initial spike, the main body of the high-energy emission. Still extraordinarily bright, pouring out the energy liberated by the sudden magnetic reconfiguration we discussed. This is the fireball, in a sense, the flood of high-energy light created as the accelerated particles and heated plasma radiate away their energy. And then comes the third act, the most revealing and beautiful part of all, the pulsating tail. After the initial spike and the main burst, the flare doesn't simply switch off, Instead, it settles into a longer-lasting glow that gradually fades over many seconds, sometimes several minutes, and remarkably, this fading tail pulsates. It brightens and dims in a steady rhythm. And here's the extraordinary thing about that rhythm. Its period matches the rotation period of the Magnetar itself. The tail pulses in time with the spinning of the star. Why? This is one of those places where a single observation reveals the whole physical picture. So let me walk through it carefully, because it's genuinely elegant. When the giant flare erupts, it creates a vast amount of hot plasma, superheated charged material, right at the surface and in the region just above it. Now, recall the Magnetar's defining feature, its colossal magnetic field. That field is so overwhelmingly strong that it can trap this hot plasma, confining it, holding it in place near the star, anchored to the magnetic field. The plasma can't simply fly away, because the magnetic field grips it and holds it close, like a hand cupping a glowing ember. So after the initial explosion, you're left with a trapped, glowing cloud of hot plasma, held near the surface of the star by the magnetic field, radiating away its energy as it slowly cools. This trapped, radiating plasma is what produces the tail, the lingering glow after the main burst. But the star is spinning, and the trapped plasma is anchored to a particular region of the star on one side, held there by the field lines rooted in that part of the surface. So as the Magnetar rotates, it carries this glowing region of trapped plasma around with it, sweeping it toward us and then away from us, toward us and then away once every rotation. When the bright, glowing region is facing us, we see the tail brighten. When the star's rotation carries that region around to the far side, out of our view, we see it dim. Then it swings back into view and it brightens again. The pulsation of the tail is simply the rotating star carrying the trapped emitting region in and out of our line of sight. The tail pulses at the star's rotation period because we're watching a glowing patch, fixed to the surface, being swept around by the spin. It's like a lighthouse, but instead of a beam, we're watching a glowing hotspot rotate into view and out again. And this is a wonderful confirmation of the whole physical picture we've built. The pulsating tail tells us directly several things at once. That a giant flare creates hot plasma, that the magnetic field is strong enough to trap that plasma near the star, and that the star is rotating with the particular period, which we can read straight off of the pulsation. 3 pieces of physics, all revealed by watching the rhythm of a fading glow. The tail is the star, in effect, telling us about itself. The magnetic field's grip and the star's spin written into the flickering light. Now, let me ground this in a real event. The most famous giant flare ever recorded, because it makes all of this concrete and shows just how far the reach of one of these eruptions extends. On the 27th of December 2004, a giant flare erupted from a magnetar called SGR 1806-20, a soft gamma repeater sitting roughly 50,000 light years away on the far side of our own galaxy, near the galactic center. 50,000 light years is an immense distance, most of the way across the entire Milky Way. And yet, when that flare's light reached us, after 50,000 years of travel, it was so intense that it briefly affected instruments here at Earth. Let me make that vivid, because it's genuinely staggering. This flare, from halfway across the galaxy, delivered a pulse of radiation that momentarily disturbed Earth's upper atmosphere. It ionized part of our upper atmosphere, the way the sun's radiation does by day, except this came from a dead star 50,000 light years away, in a burst lasting a fraction of a second. Spacecraft and satellites designed to detect gamma rays were briefly saturated, overwhelmed, some of their instruments swamped by the sheer intensity of the pulse. For an object so far away that its light took 50,000 years to reach us, an object we cannot even see with the naked eye, to reach across all that emptiness and physically perturb our atmosphere and our satellites, is a testament to just how violently concentrated the energy of a giant flare truly is. In that initial spike, lasting a fraction of a second, SGR 1806-20 released more energy in high-energy light than our sun pours out across 100,000 years, and it did it in an instant from the far side of the galaxy, and we still felt it. That reach is why giant flares matter, and it's also where we have to be very careful and very honest, because it's easy to slide from awe into alarm, and alarm here would be misplaced. Let me be clear and calm about the question everyone naturally asks. Is this dangerous to us? Do the known magnetars pose a threat to Earth? The answer for the known magnetars is no. There is no imminent danger to Earth from any magnetar we currently know about. The magnetars we've catalogued are far away, thousands of light years distant, and at those distances, even a giant flare, while detectable and even capable of briefly nudging our atmosphere and dazzling our satellites, does not threaten life on Earth. The 2004 flare from SGR 1806-20, dramatic as it was, briefly disturbing our upper atmosphere from 50,000 light years away, caused no harm to anyone. Our atmosphere and magnetic field absorbed the pulse. Life went on entirely unaffected. So I want to say plainly, the known magnetars are not a threat hanging over us. They're distant, and distance is enormously protective, because the intensity of radiation falls off dramatically with distance. Please don't come away from tonight afraid of these objects. They are wonders to understand, not dangers looming over your daily life. But I also don't want to be dishonest by pretending distance makes them harmless in principle, because it's the distance specifically that protects us and that lets us ask a legitimate physical question. What if a giant flare happened much closer? This is a fair scientific question, and the answer is instructive. If a magnetar were to produce a giant flare while sitting very close to us, within a handful of light years, say, close enough that the intensity hadn't spread thin over vast distances, then the pulse of high-energy radiation arriving at Earth could be genuinely hazardous. It could significantly damage our atmosphere's protective ozone layer, and a strong enough burst of X-rays and gamma rays could have serious consequences for the biosphere. That's a real physical possibility in principle, but, and this is the crucial point, there are no known magnetars anywhere near close enough for this to be a realistic concern. Magnetars are rare. We know of only about 30 in the whole galaxy, and none of them are anywhere near our cosmic doorstep. The dangerous scenario requires a magnetar within a few light years producing a giant flare, and we have no such object nearby. So the hazard is real as physics, but entirely hypothetical as a practical matter. It's the kind of scenario that helps us understand just how powerful these events are, not a warning about our actual circumstances. Distant giant flares are spectacular and harmless to us. A hypothetical very close one would be dangerous, but no such close magnetar exists. Both of those things are true, and holding them together is the honest way to think about it. Now we come to the heart of the title, the claim that a magnetar flare can be, in a specific sense, more violent than a supernova. And this is where I have to be extremely precise, because there's a version of this claim that's simply false, and a version that's genuinely remarkably true. And the difference between them is everything. Here is the false version, the one I want to rule out clearly. A giant magnetar flare does not release more total energy than a supernova. That's not true, and I won't claim it. A supernova, the explosion that creates a neutron star in the first place, is one of the most energetic events in the entire universe. When you add up everything a supernova releases, and this is important, you have to count not just the visible light, but the kinetic energy of the ejected material, blasted outward at enormous speeds, and above all the neutrinos, those ghostly particles that carry away the overwhelming majority of a supernova's energy, an almost unimaginable flood of them. When you tally all of that, the light, the kinetic energy of the ejector, and the vast torrent of neutrinos, a supernova's total energy release utterly dwarfs even the greatest giant flare. In total energy, it's not even close. The supernova wins overwhelmingly. So if someone tells you a magnetar flare is simply a bigger explosion than a supernova, releasing more total energy, that's wrong. And you should know it's wrong. So in what sense is the title true? Here it is. And it's a genuinely profound distinction. A giant magnetar flare can be more violent than a supernova, not in total energy, but in instantaneous intensity, in the abruptness and concentration of its electromagnetic output. Let me unpack that carefully, because it's the whole point. Consider timing. A supernova's energy, enormous as it is released over a considerable stretch of time. The explosion unfolds, the light rises over days and weeks, the neutrinos pour out over seconds to minutes, the ejector expands over years. The energy, though colossal in total, is spread out. Now consider a giant flare's initial spike. That spike releases its energy in a fraction of a second. Not days, not weeks, not even seconds. A fraction of a single second. And it concentrates that release into electromagnetic radiation, into a blast of X-rays and gamma rays, rather than spreading it across neutrinos and slow-moving ejector. So while the flare's total energy is far less than a supernova's, the rate at which it pours out that energy, the sheer instantaneous power, the energy per moment, can be extraordinary. And in that narrow but very real sense, its peak electromagnetic intensity can rival or even momentarily exceed aspects of the explosion that made it. Think of the difference between a large reservoir emptying slowly through a wide river over days, and a smaller tank emptying all at once through a burst dam in a single instant. The reservoir holds far more water in total, no question. But at the instant the dam bursts, the rush of water in that one moment, the violence of that instant can be more intense than anything happening at the placid river. The magnetar flare is the burst dam, less total energy, but released so abruptly, so concentrated in time and in the form of high energy light, that its instantaneous violence is breathtaking. That's what more violent than a supernova means, correctly understood. It's a statement about suddenness and peak intensity and the concentration of electromagnetic output, not about total energy. The flare doesn't out-energy the supernova. It out-abrupts it. It packs its punch into a sliver of time so thin that, for that sliver, the intensity is almost beyond comparison. And here is a fact that makes the magnetar even more astonishing and sharpens the whole point. The magnetar survives. This is not a second supernova. the star does not explode apart. It does not undergo another catastrophic collapse. It does not tear itself to pieces. A giant flare, for all its instantaneous violence, is the release of energy from a star that remains physically intact afterward. Still sitting there, still spinning, still carrying its magnetic field, having simply paid out a portion of its enormous stored magnetic energy. The Magnetar convulses, unleashes one of the most violent electromagnetic events in the galaxy, and then, remarkably, settles back down and carries on. The city-sized star endures. That's a crucial part of understanding what a magnetar flare is and what it is not. It is not the star exploding. It is not the star dying again. It's the star surviving a violent release of its own magnetic energy, staying whole through an event that, for a fraction of a second, rivals the intensity of the great explosions that create these objects. What does the Magnetar lose in the process? It loses some of its stored magnetic energy. That's the reservoir being tapped. Each giant flare, and each smaller burst too, draws down the star's magnetic energy, unwinds a little of the tension coiled in its field. And this has a long-term consequence. Over its lifetime, through repeated bursts and the occasional giant flare and the constant slow decay powering its persistent glow, a magnetar gradually depletes its magnetic reservoir. The field decays, weakens, unwinds, and as it does, the magnetar's activity gradually fades. A young magnetar, freshly minted with a monstrous field, is a violently active object, crackling with bursts. But over thousands and then millions of years, as the field decays and the reservoir drains, the eruptions become rarer and weaker. The persistent glow dims, and the magnetar slowly quiets down. It ages out of its violent youth. Eventually it may become a faint, quiet, largely dormant neutron star. Its once terrifying field decayed to a shadow of its former strength, its dramatic career behind it. The magnetar phase, it seems, is a stage, a violent chapter in the long life of certain neutron stars, powered by an extreme field that cannot last forever, and that pays for every eruption out of its own dwindling store. Let me now tie together some threads that have been running through our whole exploration, because there are a few connections that place magnetars in the broader landscape of astronomy and that reward understanding. For years, astronomers observed several different kinds of puzzling objects and gave them different names, before realizing they were all facets of the same underlying reality. Some objects were seen producing repeating bursts of soft gamma rays, and these were called soft gamma repeaters, SGRs. Others were seen as X-ray pulsars that were anomalous, that didn't fit the usual pattern of being powered by rotation or by a companion star, and these were called anomalous X-ray pulsars, AXPs. For a time these seemed like separate mysteries, but as understanding grew, it became clear that both the soft gamma repeaters and the anomalous X-ray pulsars are fundamentally magnetars. They're the same kind of object, extreme magnetized neutron stars, seen through different observational windows, showing different faces of the same magnetic engine. The soft gamma repeaters are magnetars caught in their bursting behavior. The anomalous X-ray pulsars are magnetars observed through their persistent X-ray glow. Today, these once separate categories are understood largely within the single broader framework of the Magnetar. What looked like two mysteries turned out to be one, and recognizing that unity was a real triumph of understanding. It's worth adding that a given magnetar can show both behaviors. glowing persistently in X-rays and producing gamma-ray bursts, further underlining that these labels describe behaviors and viewing angles, not fundamentally different objects. There's another connection worth exploring, one of the most exciting frontiers in recent astronomy: the link between magnetars and fast radio bursts. Fast radio bursts, or FRBs, are extraordinarily brief, extraordinarily bright flashes of radio waves that arrive from across the cosmos, lasting mere thousandths of a second, and for years their origin was a genuine mystery. What could produce such intense, such rapid bursts of radio energy? A number of ideas were proposed, and the puzzle deepened as more were detected. Then came a striking development. A magnetar in our own galaxy was observed producing a burst of radio waves with characteristics resembling the fast radio bursts seen from far away. For the first time, a magnetar was caught producing an FRB-like signal, providing direct evidence linking at least some fast radio bursts to magnetar activity. This was a major breakthrough, tying these mysterious cosmic flashes, at least in part, to the violent behavior of magnetized neutron stars. But I have to add an important qualification here, and it's one of honesty about the limits of what this shows. This connection does not mean that every fast radio burst comes from a magnetar. That would be claiming far more than the evidence supports. What we can say is that at least some fast radio bursts have been associated with magnetar activity, that magnetars are demonstrably capable of producing such signals. But the population of fast radio bursts is diverse. Some repeat, some don't. They come from many different environments, and it remains entirely possible, even likely, that more than one kind of source produces them. Magnetars are one confirmed contributor, perhaps a major one, but the field is careful not to declare that they are the sole origin of all fast radio bursts. So the honest statement is this: magnetars can produce fast radio bursts and are linked to at least some of them, but not necessarily to all. It's a real connection, genuinely exciting, and appropriately bounded. I also want to draw one more careful boundary, because it's a common point of confusion. Magnetar giant flares are not the same as classical gamma-ray bursts. Both involve bursts of gamma rays, and a distant giant flare can briefly resemble one. But classical gamma-ray bursts are a separate class of phenomenon, associated with entirely different events. The catastrophic collapse of massive stars, or the merger of compact objects, releasing energies on a completely different scale. A magnetar giant flare is its own distinct thing. The release of magnetic energy from a surviving neutron star, and it should not be conflated with those far more energetic cosmic explosions. Keeping these categories distinct is part of understanding what a magnetar flare truly is, and what it isn't. Now, how do we study any of this, given that we can never visit a magnetar, never cut one open, never watch its interior directly? The answer is that we read the light, and we read it with remarkable ingenuity. Every aspect of a magnetar's radiation carries information about the hidden physics. The timing of the burst tells us about how stress builds and releases. The spectra, the distribution of the radiation across different energies, tell us about the temperatures and processes and magnetic conditions at the emitting regions. The pulse patterns, like that pulsating tail, tell us about the star's rotation and the geometry of the trapped plasma and the field. And sudden changes in the star's spin, tiny jumps in its rotation rate that sometimes accompany bursts, tell us about the coupling between the crust and the interior, hints of the mechanical events happening at the surface. From all of these timing, spectra, pulse patterns, and spin changes, astronomers reconstruct a picture of what's happening inside and around an object they can never touch. It's a beautiful piece of scientific detective work, inferring the hidden interior from the patterns in the light that escapes. And what magnetars reveal, through all this careful study, reaches far beyond the objects themselves. They are natural laboratories for physics we could never reproduce on Earth. By watching how and when a magnetar's crust yields, we learn about the strength and structure of neutron star crusts, about how the strongest solid matter in the universe behaves under stress. By studying the persistent glow and the bursts, we probe the properties of ultra-dense matter, the exotic states that exist only in neutron star interiors, states we cannot create in any laboratory. And by observing the effects of fields 100 million times stronger than anything we can build, we test how matter and light and space itself behave under magnetic conditions found nowhere else. Magnetars let us study the strength of neutron star crusts, the nature of ultra-dense matter, and the behavior of magnetic fields at the very edge of what physics permits, all by watching the light from a dead star the size of a city. But I'll return one final time to the distinction that has run like a spine through our entire journey, because it's the mark of honest science and the truest thing I can leave you with. We must always separate what we directly observe from what we model. We observe with confidence the persistent X-ray glow, the short bursts, the rare giant flares, the pulsating tails, the spin changes, the spectra. Those are measured facts, light that reached our instruments. But the story we tell about the interior, the tangled internal field, the crust yielding under magnetic stress, the field lines reconnecting, the precise sequence of a flare's trigger, that's a model, a theoretical reconstruction built to explain the observations, well supported and coherent, but not directly witnessed. We have never seen a magnetar's crust shift or its field reconnect. We infer these things, reasonably and rigorously, from the light and from the physics, and genuine uncertainties remain inside that model about the exact origin of the fields, the precise behavior of the crust, the detailed trigger of the flares. Holding the confidence and the uncertainty together, honoring both, is what it means to understand a magnetar honestly. So let me draw the whole picture together. The single continuous chain we've followed from beginning to end, because it's one story, not a list of facts. A massive star dies, its core collapses in a supernova, and it leaves behind a neutron star, a city-sized object heavier than the sun. In rare cases, through a dynamo at birth, or an inherited and concentrated field, or some combination we're still working out, that neutron star ends up with a magnetic field 100 million times stronger than anything we can build. The strongest field tied to any known stellar object, likely far more tangled and powerful inside than the smooth field we measure outside. That field is the star's dominant energy reservoir, distinct from its heat, its spin, and the long-gone energy of its birth explosion. As the field slowly decays, it powers a persistent X-ray glow across thousands of years, and it breaks the star's rotation so hard the magnetar spins surprisingly slowly. The field, straining to rearrange itself, places mounting stress on the rigid crust until the crust yields in a starquake, dragging the rooted field lines and twisting the magnetosphere, loading it with energy. When that stressed field suddenly reconfigures and reconnects, It accelerates particles and hurls out an intense burst of X-rays and gamma rays. Most such events are small. The rarest are giant flares whose brief initial spike, intense high-energy release, and rotation-linked, pulsating tail from trapped plasma make them, for a fraction of a second, rival the very explosions that create these objects, not in total energy, but in sheer instantaneous, concentrated violence. And through it all, the Magnetar survives, intact, having spent a little of its stored magnetic energy, destined to slowly quiet as its field decays across the ages. That's what a Magnetar really is. A dead star the size of a city, powered not by fire but by magnetism, capable of a violence so sudden and so concentrated that it can reach across the entire galaxy to brush against our world, and yet survive its own eruption whole. Not a second supernova, but something stranger and, in its own narrow and remarkable way, more violent still, a rapid release of magnetic energy from a neutron star that remains, against all that fury, physically intact. Thank you for taking this journey with me tonight, down into the crust of a dead star and out into the fury of its magnetic field. If you found it worth your time, a like or a subscribe genuinely helps this channel keep exploring the strangest corners of the cosmos. And the next time you look up at the quiet night sky, remember that somewhere out there, hidden and silent, a city-sized corpse of a star holds a magnetic field strong enough to crack itself open, waiting, holding its tension, one of the most violent objects the universe has ever made. Good night.